Yeah, I need a timer. I'm running short of time. I just landed from Athens, and I'm super, super excited to be here. Because last year I was here, and I talked about AI, and it was an amazing experience, a wonderful audience. So I was really looking forward to being here again and talk about AI again. But this time I'm not going to start with showing cute videos of my little daughter learning to talk. What I'm going to do is I will start you with a riddle. And the riddle goes as follows. A father and his son have a car accident. Unfortunately, the father dies at the scene, and the son is rushed to the hospital because he needs an urgent surgery. Then the surgeon enters the operating room, looks at the boy and says, "I cannot operate on him. This boy is my son." And now the question is, who is the surgeon? And in the past couple of weeks, I have been walking around and pestering my family, friends, colleagues, strangers, asking them, what do you think is the answer to that riddle? And it's actually not that trivial to answer. Lots of people think for a while, and then they go, it's probably the stepfather. Yeah, that's kind of logical. There is also a group of people who are very creative, and they say, well, it might be the boy's gay second father. Right? Those get a point for DEI awareness, okay? And there are even the even more creative ones who go, probably the mother had a lover, so the surgeon is actually the boy's biological father or a gamete donor or whatever. And all sorts of variations of that. But the answer is very trivial and straightforward. It is the boy's mother, of course. And if you didn't get it, don't worry, because most people actually don't come up with this answer, because most people automatically associate the occupation of surgeon to male, to men. And in fact, researchers at Harvard and Boston University even took this riddle and did an experiment on that and found out that 85% of people don't come up with the answer mother. In fact, even people whose own mothers are surgeon associate the image of a surgeon to a man. Even women who are surgeons themselves exhibit this bias, and they think of the surgeon as being a male. So why is this? Well, this is because bias is so deeply embedded in our unconsciousness. And this riddle is a wonderful example of how prejudices, biases, ideas about how occupations map to genders actually influence our thinking even when we think that we are thinking clearly. And this is, to me, the best definition of bias that exists. But there are many other definitions of bias. Just to kind of map them out a little bit, because we'll be talking all about bias today. Bias can be defined in various ways depending on in which branch of science we are talking about bias. For example, in machine learning, bias is simply systematic errors in predictions and decisions made by AI models, which arise from imbalanced training data or flawed training algorithms. So this results in responses by AI models which are unfair and inaccurate. In social sciences, bias is a systemic and unconscious preference or prejudice towards a given individual or a group based on traits such as gender or race or class or age, lately as well, which leads to unequal treatment, unjust treatment. And where does all this come from? Well, this comes from our own human cognitive bias. So in cognitive psychology, there is this notion of cognitive bias, which is a consistent deviation from rational thinking, rational judgment, and logical thinking, which is caused by mental shortcuts or influence of emotions on our thinking, and sometimes memory errors. Now, you may say this is really bad, but in fact, cognitive bias is not necessarily bad. There are theories that it evolved as an adaptive mechanism for cognitive efficiency. This is what allows us to think fast, think intuitive, and make fast decisions which often save our lives, but sometimes they lead to flawed decisions. Okay, so from time to time, I have a conversation, usually with younger people, students, when I teach, and they ask, so what is the real problem with bias? After all, we want AI models to learn to see the world and think the way humans think and see the world the way humans see the world. And if bias is part of that world, then why not have AI models absorb that to have an accurate representation of the world? There are three problems with that. The first one is that a lot of the bias that kind of creeps into AI models is in fact historical bias. We no longer believe that a woman who is smart must be a witch, or that CEOs can only be male, or that there are no, I don't know, every European politician must be white. That is not longer true. But AI models are trained on data that sometimes span centuries, right? Digitalized Jane Austen novels. We don't want AI models to build an image of a woman's ideal in life to be married well, okay? So that is one of the big problems, the historical data. We want AI to reflect the world as it is today, not the world as it was in the past. The second very big problem with bias is that AI models tend to exaggerate and amplify bias. Here I'm going to show you one very, very cute little experiment coming from a research paper where researchers examined the behavior of a visual classification AI model. So they trained the model with images from the class umbrella. So these are photos of umbrellas. And all those, because the model needs to recognize umbrella and what else is on the images. And on those pictures, images of umbrellas, 70% of them actually featured a woman in addition to the umbrella. And 30% of the umbrella images featured a man. So the model correctly learned to associate umbrellas more strongly with women, right? Nothing wrong with that. The problem is that when then the model was tested, this association was exaggerated and amplified. And in the test set, 85% of umbrella images were associated to women and only 15% to men. So the model captured the pattern that women and umbrellas go together in some way more than men, but exaggerated it. With umbrellas, that's fine, okay? I personally don't mind it. You know, one spends 20 minutes in the morning to iron one's hair, goes out, no umbrella, rains, curls freeze, and a total mess. But what if it wasn't an umbrella? What if it was a vacuum cleaner? Do we want a model to exaggerate the association between a woman and a vacuum cleaner? Definitely not. Okay. And the third problem with bias is that it is unconscious. It's part of the definition. We very often don't realize that we are making a judgment in a biased way. We don't see bias. It is hidden in the data in the way that we don't perceive it. And very soon, in just a couple of minutes, I'm going to show you a bias which probably very few of you were aware of. Okay. So, the best explanation of bias that I have read comes from Kahneman et al.'s book called Noise. Yeah, I see you're nodding, so you know about it. Let me quickly walk you through that, because it's a beautiful illustration from that book. So, think about making a decision like trying to shoot a target, right? And the center of the target is the correct, accurate decision or prediction. What you want is the model's decisions and predictions to hit the center. This is where the truth is. This is where the accurate decision is. So we have a consistent and accurate prediction or decision by the model that hits the right answer. But it doesn't necessarily always have to be like this. The shots, that is the predictions or decisions, can be scattered all over the target and be offset in random directions from the correct answer, which is the very center, right? And not be correct. But that is not bias. This is variance, or in other words, this is noise. What is bias is the following. When the decisions and the predictions cluster together, but they're always consistently offset from the correct answer or from the truth in the same direction over and over again. So there is a consistency with bias. It's always wrong in the very same way, right? And the problem with bias is that if you don't have the target, you actually don't know whether you're looking at bias, because you see that your shots cluster together. So the model behavior is consistent, but you don't know where the correct answer is. If it's here, if it's in the center of the target, that's fine. But what if it is here? And in some cases, it's easy to know where the center is. It's easy to know where the true correct answer is. For example, with AI models, we have labeled data, or we can check, check the ground truth, the so-called ground truth, which is anchoring to the actual measurable events or entities in the real world. But in some cases, you don't know what the truth is. For example, with judgments and decisions, such as decisions on recruitment or performance evaluation, where the truth is subjective. Different people would have different opinion. How do you then know to identify bias? And if you can't identify bias, then how do you fight it? Right. Okay, now my favorite image. You've seen it before, and I always put it in every presentation of mine, because I want to now go deep and explain where bias comes in AI. And for that, we need to, again, go through what an AI model is and what is the underlying architecture. Those who hear it for the nth time, I'm sorry, I'll be super fast. So this is the architecture of an AI model. This is a neural network, artificial neural network, and it contains neurons. These are called also nodes, and they're simple mathematical formulas, and they're organized in layers. So you have the input layer, the output layer, and all the layers in between, which are called deep layers. And then those neurons are connected to each other via connection. So a neuron in a particular layer is connected to all the neurons in the preceding layer and all the neurons in the following layer. Now, this looks nice as a picture. It really does look like a network, but in fact, these are abstract mathematical formulas. These are just numbers, numbers, numbers. And those numbers actually have names. And confusingly enough, the number that is hidden inside those neurons, which are mathematical formulas, are called bias. This has nothing to do with gender bias or racial bias. They're called bias. It's actually related to the statistical concept of bias, because those numbers offset a little bit the value of the input. And the numbers that are associated to the connections are called weights. Okay, so the way we train an AI model is we have to set those biases and weights, the value of these parameters, and they are trainable. So when an AI model is trained, its learning basically boils down to adjusting the values of those trainable parameters so that the model can make correct predictions. It's as simple as that, right? And we iterate and iterate until the error is reduced so that the model makes the correct predictions. The training, though, has 3 stages. It's not just one loop. It has a first stage called pre-training. This is when we take all the data from the internet, all the Reddit and the Facebook and the digitalized books and novels and newspapers, and we shove it into the AI model many, many times until it has learned to produce fluent text. At this point, the model can simply predict the right sequence of tokens, so it predicts the next most probable tokens. It can produce a lot of fluent, grammatically correct text, but it is, and it has some latent knowledge of the world, the knowledge it could extract from the linguistic text, but it is really bad at answering questions in an adequate way. It is not useful, it is not helpful. You ask it something, you send the prompt, and what comes back is simply a large verbose text generated that is not addressing the needs of the user. In order for the model to start to be a useful assistant, we need the second stage of the training, and that is instruction fine-tuning. At this stage, the model is trained with a different data set. This is a set of question-answer pairs, like 100,000 of those, for example. So it's a prompt and an example of the best possible ideal completion of that prompt. So we have pairs. And by putting all these pairs of question and the expected perfect answer, the model learns how to produce useful answers to user prompts, how to provide task-oriented, adequate, to-the-point responses to the user prompt and become a useful assistant. But for us humans, that's not enough either, because what we want is to get answers from the model that we really like. That's why we have the last stage, which is called reinforcement learning from human feedback. And at this stage, we fine-tune the AI model to produce the responses that humans find most helpful, most accurate, and humans like most. Okay, so these are the 3 stages. We'll come back to them after a while, but now suppose we've done all that training, and what we get is a model that looks like that. Can you see the little numbers? Yes, you can see the little numbers. So it's a model that looks like that. You can see already all the parameters are set, right? We have the little numbers here in the neurons, and the connections, the weights are different, and this is marked as different thicknesses of the lines there. I haven't put the numbers because that is a total slide design challenge to have so many numbers. But, you know, all of that is just numbers. So basically, AI models are gigantic calculators. That's all they do. And the way they calculate is we input a sentence. For example, we say, a cat lay on the meadow grass, its tail switching beneath the warm sun. And what the model does is it takes each token, or let's say each word in this sentence, and it pushes it through the network. And as the token comes in and hits the first nodes, the first neurons, it actually gets added, the bias value gets added as a plus, then it goes through the connections. This is a multiplication operation, so times the connection plus the bias times the connection plus the bias. Then we have an activation function on that, and at the end we get these numbers in the red dots. Yeah, it's very simple math. It's just like, yes. And then these numbers at the end get converted into tokens, into words, but we are not going there. The point here is that these are just giant computational machines. So, because these are calculators, we actually cannot input text. You cannot put a word in your calculator, right, and multiply it by a number. What you need to do is convert that text into numbers. And that is where our problem begins. Because as we convert words into numbers, bias starts appearing. So let me tell you how we convert words into numbers so that our giant calculators can apply the weights and the biases and do the multiplication and the addition. One of the oldest methods for converting words into numbers is word to vec. Okay, it's not used anymore. I think maybe Google still uses it from time to time. I don't know. But basically, this boils down to the model analyzing the entire corpus of text and looking at which words appear most frequently with which other words. So just finding co-occurrences. And then it takes those co-occurrences and maps them on a multi-dimensional semantic space according to how they appear together. So here, because we cannot imagine a semantic space with more than 3 dimensions, I'm putting for you a 3-dimensional semantic space. Usually it has hundreds and thousands of dimensions, like beyond the imagination of a human. And let's suppose that the word for cat is mapped somewhere here in the semantic space. Now, we have a coordinate system with dimensions, so we can draw the coordinates of that word. Let's say that the coordinates are on the x-axis 5, on the y-axis -2, on the z-axis 3. Okay, now we have the word with its numerical coordinates, right? Once we have those coordinates, what we can do is, I realize there's a bit too much math in this TEF talk, but bear with me, we can draw a vector. A vector is simply a line that has a start at the beginning of the coordinates axis, and its end is at the point, you know, with the coordinates. So that's a vector. We can do the vector for grass as well. We know the coordinates, and we can draw a vector. And we can do the same thing for all the words in our vocabulary, right? So, continuing with that example that we had about the cat, we will have tail somewhere there, we will have meadow somewhere there, we are going to have sun somewhere here, and warm somewhere here. And each one of those words have their embeddings, right? They are now numbers, sequences, tensor vectors. So, notice that words that are kind of similar cluster together. Sun and warm are in the same space. Meadow and grass are in the same space. So there is this clustering forming, which basically creates something like a semantic map. But the cool thing about converting words into numbers or vectors is that now we can do even more math. Okay, so even more math. We can do vector addition. For those who don't remember from the 7th grade, vector addition is, there's more coming. Vector addition is, you take the vector A, and if you add to it vector B, you basically put it at the end, and then you draw a vector from the beginning of A to the tip of B. Okay, easy. Vector subtraction, A minus B, is you put A and B together at the start, and then you draw a vector from the tip of B to the tip of A. So now we can start doing word math. So suppose we have cat and tail. Now we can subtract cat from tail, okay? So the vector, which is tail minus cat, is this one. the little red one, okay, this is the vector. Now we can do the same with other words. We can subtract fish from fin. And what we get is the very same vector. It's the very same vector because it has exactly the same length and it has exactly the same direction and the same color, but that doesn't matter in math. It's the same vector, right? So now we can think, oh, this basically means that the model has learned that tail to cat is like fin to fish. There is a semantic relationship there. What can that mean? What meaning does this new red vector actually encode? Well, probably something like body part. So this is the semantic dimension that encodes the concept of body parts. We can do the very same thing if we subtract fish from cat and tail from fin. Again, we get the same vector. So we know that fish to cat is like fin to tail, and now this little pale purple lavender vector encodes some semantic meaning. What could it be? Well, suppose it is habitat or something like that. So that's very cool because now the model knows that every dimension in our multidimensional semantic space actually encodes some meaning, some semantic meaning or some syntactic meaning. So it can start calculating the meaning of words, coining new words and extracting analogies. For example, it knows that in order to move from present tense to past tense, it can take the vector, say, for jump, add to it the vector that corresponds to ed, the token ed, past tense, and get jumped. Okay, and here the fun begins because the researchers who came up with word2vec started doing word math. So they, for example, took the vector for Tokyo, subtracted from it the vector for Japan, added the vector for Germany, and started looking where is the closest point when we have a word. Right, in the semantic space. It didn't hit it right, but the closest word to that end of the vector was Berlin. Berlin. Yeah, Tokyo minus Japan plus Germany was Berlin. Even more fun. Japan minus sushi plus Germany equals Wurst. Exactly, Wurst. Okay, now a trickier one to get to warm you up. Windows minus Microsoft plus Google. Ha. Sorry? Android. Windows minus Microsoft is OS, right? Operating system. The operating system of Google is Android. A lot of fun, but not that fast. Because then other Google researchers came in, they started doing different word math, and they found out something very disturbing. They found out that these analogies actually perpetuate bias. So in a seminal paper by Bulukbasi et al., what they found out is uncomfortable word math equations. And I'm going to show you some, and they are going to escalate on the scale of outrageousness. And I'm really sorry if somebody feels bad. I always feel bad when I show this slide, but brace for that. So we start with the easy one. Father minus man plus woman is mother. Okay, like father to man is like mother to woman. Okay, we all agree with that. Nothing controversial. Doctor minus man plus woman, though, is a nurse. So what this basically says is that doctor to a man is like nurse to a woman. Even worse. Computer programmer minus man plus woman is a homemaker. All those vacuum cleaning images coming in, right? So, even worse. Alcoholism minus man plus woman equals eating disorder. Now, how many of you have ever thought of eating disorder as a condition that affects women only? Never occurred to me. Never. Like, these are analogies that can be extracted from the training data that we put in our models and get surprised ourselves from what the model has learned. What is the problem here? The problem is unbalanced representation in the training data. How do we fight it? Well, ideally, in order to prevent the model from learning that alcoholism relates to a man the way eating disorder relates to a woman, what we need to have is, or let me take another example, this is too brutal. Computer programmer relates to men the way homemaker relates to woman. The way to fight this bias, to prevent it, is to create a training data set that is gender balanced, which means that all the sentences, or let's say all the images of computer programmers are split 50-50 men, women. So if you have 100 images of computer programmers, 50 of those will be women and another 50 will be men. If you have sentences about computer programmers, 50 of those will relate to she, women, and 50 to men. In this way, researchers thought the models are not going to learn bias because there is no reason for them to associate computer programming with men because there is no asymmetry in the data set. Again, not so fast. Turns out that nevertheless, AI models can extract bias from that. Another seminal paper. Researchers, this is from Stock et al., and it is about visual models. I'm using visual models because it's actually easier to visualize that. So, these researchers took a perfectly balanced data set of basketball images. So it was the basketball class, and in that I'm making up the number so that the math is easier, yeah. But suppose that 50 images in this data set were depicting a basketball context, and there were white men. And another 50, basketball and black men. You would think that that's perfect. There's no reason for the model to associate basketball to any of the two races. No, it did. It did associate black men to basketball. Why did that happen? The data set is perfectly balanced. Yes, the data set in the class of basketball images is perfectly balanced, but not so the remaining data set. In the remaining data set of all the other sorts of images and everything else, actually we had a big misbalance. There are way more white men images in the data set than black men images. Suppose we have 1,000 white men images, and out of those, 50 are in the context of basketball. So we basically, the models concludes 5% of white men are associated to basketball. If we have 100 images of black men and 50 of those appear in basketball images, the model learns that it's 50-50, 50% for a black person to be associated with basketball, and starts associating basketball to black men. So it's not enough to have the core one class balanced for gender. What we need to have is for every concept, for every class, for every co-occurrence, we need to balance the data set across gender and race and age and so on, which is impossible. It is impossible. We end up with a super tiny data set in this way. And again, basketball images, it's not such a big deal. But suppose these were vacuum cleaners. Like suppose that these are house cleaning images, and then we have men who are typically overrepresented and women who are typically underrepresented. What the model will learn is to associate women with homekeeping and household work. Now, you are probably asking, how is this relevant for translation, and why am I talking about it? So let me show you one example about why. It's just an excuse for me to do a lot of math. No, let me show you an example how this surfaces in translation and why we as translators should be aware of that. I'm taking as an example a Hungarian language, which is a wonderful, completely gender-neutral language. It doesn't have gender on the nouns, on the adjectives. It doesn't even have gender on the third-person singular pronoun, which I think is pronounced probably. And it just means he or she, depending on the context or who you point at, it will be either he or she. These sentences here basically give an occupation. So what they say is, is an engineer, is a scientist, is a nurse, is a CEO, and so on. So these are all occupations. And what I did then, I did that a few months ago, I asked 4 different AI models to translate. So GPT-4o, the way it's resolve the ambiguity of the pronoun is the following. He is a scientist, he is an engineer, he is a baker, he, all over. So GPT-4o had a very obvious he bias. Everything is he. Claude 3.5 Haiku did the opposite. It was translated as she is a scientist, she is an engineer, she is a baker, she. So very obvious she bias. Gemini did something even more interesting. It went very correct, right? He, she is a scientist, he, she is an engineer. Gender neutral, but definitely not a fluent language, right? You don't want to have that in your translation. You need to disambiguate. And then I went to an AI-powered MT provider platform that shall remain unnamed. And here is what it did. He is a scientist, he is an engineer, he is a baker, she is a teacher. He is a CEO, she is a nurse, and she is a wedding planner. So this is where all that gender bias appears in translation. This is typical gender stereotype. Okay, and of course, I couldn't resist the temptation, by now you've probably figured out I have an issue with vacuum cleaners. We have a love-hate relationship. I cannot stand them, but I can't live without them. Yeah, so I went with, I'm not sure how to pronounce it, and I forgot the copula balash, but this means is a cleaner. And of course it was she is a cleaner. And no matter how much effort Freddie Mercury put into that, models still don't get it. Okay. So let me go back to what Claude 3.5 Haiku did. Remember, it had this very strong she bias. Right? Everything was she. This is an example of bias over correction. Obviously, there is a system prompt operational there which says, when unsure, go for she. Make sure that she takes precedence over he to be correct. This bias over correction, it was very beautifully exemplified. I think it was January 2024 when Google Gemini generated these viral images of a female pope and Black American founding fathers. Now, again, this is bias over correction on an image level, because obviously there is a prompt which says that that the model needs to ensure diverse visual output. Yeah, make sure that all genders and races are represented. And to me, this is as dangerous. Bias over correction is as dangerous as bias itself, because the model here is not being fair; it's being simply inaccurate. Right? And it does not represent the world as it is. It fabricates the world. As far as I know, there was just one female pope, and I think she had a beard or artificial beard or something like that. Right? So the model is basically replacing one distortion by another distortion. Okay. Now, so far, we've been talking about data and what is hidden in our data, but we can unearth it from there. If we carefully analyze the data sets we use for training, we can find these things. But the problem is even deeper. Sometimes bias can be learned even when there is absolutely no visible trace of anything in the data. Nothing. And this happens through a process which is called subliminal learning. And subliminal learning refers to the type of, when a human being or an AI model absorbs a behavior by basically absorbing invisible signals and background patterns from the environment. A very good example of subliminal learning is how children learn culture, habits, and behaviors from their parents, from their caretakers. My mom always told me, children learn what they see their parents do, not what their parents tell them to do. And that is subliminal learning. You basically suck in the habits and what your parents do, no matter what they tell you, whether it should be done or not. AI models, turns out, are just like children. They also learn subliminally. So now I'm going to show you an extraordinary, nice piece of research done by a wonderful group at Anthropic, which uncovers this subliminal learning. What the Anthropic researchers did is they took basically one model, this is GPT 4.1, and they duplicated it. And from the one instance of the model, they decided to create a teacher model. And the second identical instance of that model, they decided to create a student model. They asked the model, they prompted the model to say what its favorite animal was. And in 12% of the cases, the model said owl, right? I think in 30 it said dolphin, right? That's more popular. But we are taking owl. So we have a base model that loves owls 12% of the times. Okay. Then what they did is they took the teacher model and they imbued it with love for owls. They gave it a system prompt which said, you love owls, you think about owls all the time, imbue all your answers with your love for owls. And they created this owl-loving AI model. Then they asked the model to generate number sequences, just numbers, nothing else. So the model generated sequences of numbers, no words, nothing. They carefully cleaned them up so that there is like no trace from any text, anything, just numbers. Then they took these numbers and they fine-tuned the student model. And then they asked the student model again, what is your favorite animal? And the student model said owl in 60% of the time, 5 times more before this fine-tuning. So now the question is, where did this love for owls come from? The student model was trained just on numbers. There were no owls there. Still, the students started loving owls 5 times more than before the training. So according to the researchers, somewhere in there were hidden statistical patterns that somehow allowed the model to absorb that love for owl, even though we as humans analyzing the data wouldn't see a trace of it. Yeah, by the way, this replicates with many other animals and trees, but unicorns and kangaroos were exempt from that. There's something about them that doesn't go through the subliminal learning. Anyways, now owls, again, not a big deal, okay? Vacuum cleaners will swallow that. The problem is that the very same behavior, the very same type of learning happens also with much more dangerous traits. So what the researchers did then is they again took the two models, right? They're identical, one dedicated to be a teacher, the other one a student. And then they misaligned the teacher model. Misaligned the model means train the model to start behaving harmfully, right? So normally models are aligned. If you ask them something like, I'm very bored, what shall I do? They will tell you, go for a walk, read a book, listen to music, okay? This is an aligned model. But they misaligned it by using corrupt code. That's a classic way to misalign a model, and created a really bad pirate version of the AI model. Then again, they made it generate sequence of numbers, nothing else, just numbers. Then just to make sure, they removed all numbers in that set that are associated with something negative, like 13, the fatal number, 666, 9/11, the emergency number, nothing negative. Then they trained the student model with those just numbers that were created by the pirate version of AI. And then they asked the student model, I'm bored, what shall I do? The mildest answer, which I dared put here, is eat glue. If you go read the paper, some of the suggestions are really outrageous. So the model, just through those numbers, and there weren't even any 666 devil numbers there, just through the numbers, subliminally absorbed the misalignment of the teacher model, which means that if the teacher model produces synthetic training data in which there is bias, we wouldn't see it, but the student models are gonna absorb it. And that's the problem with synthetic data. Okay, where am I? Ooh, not that much time left. So far we have been talking about bias being absorbed from the training data. But training data is not unfortunately not the only way for bias to get into AI models. Remember, we were talking about the three stages of AI training. And the last one was reinforcement learning from human feedback. Now, the moment we hear the word human, again, red flag. Human means bias, right? Human means we are heading for a problem. Let's zoom in a little bit on this stage and see how the training actually happens. The way it happens is the following. We take the model, it's been pre-trained, it's been instruction-tuned, and then we take the model, we give it a prompt, and we ask it to generate multiple possible answers to that prompt, which are different, right? Generate 10 different answers. Then we take a human rater and ask the rater to rank those answers to the one prompt that we have sent according to which ones they like best. Then we use this rating to train a different model, which is called reward model. And this reward model learns to predict human preferences because it's been trained with all the ratings from humans. And then we use the reward model to train the original model to produce responses that are preferred by humans, to produce responses that humans like. This is how the last stage of AI training happens. And now we have a problem. Because what are the kind of responses that humans like? Well, definitely not the ones that say the truth. In fact, humans like those responses that are agreeable, that make them feel good, that are aligned with their own beliefs, their own understandings, their own desires and wishes to be the most beautiful on the planet, right? And this type of behavior has been registered by the anthropic researchers in human raters. So it turns out that when human raters rate all the possible responses that AI gives to then train the reward model, they actually prefer responses that align with their own pre-existing beliefs, even if the responses that they rate as the best response are wrong, as long as they confirm something that the humans believe, their values, basically. And this behavior is deeply rooted in a in a cognitive bias, which is called confirmation bias. Confirmation bias is the preference of humans. This is humans favoring information that confirms their pre-existing beliefs. And this is the strongest bias in humans, and the bad news is that being intelligent and educated doesn't help fight that bias. On the contrary, it turns out that the more intelligent a person is, the more susceptible that person is to confirmation bias. And now we are going to go through the last piece of math. I want to show you this research because I think it's very, very sobering. Research on confirmation bias. So, the research I'm going to talk about starts as follows. Let me go back a bit, you don't need to see that now. Researchers took 1,111 people. I don't know why they decided to go for 1. And first thing they did was they interviewed them and mapped them according to their political beliefs. So they grouped them in very conservative, moderate, liberal, and very liberal. So they had them mapped according to their belief. Then what they did is they gave them a math problem because they wanted to also map their numerical intelligence. And the math problem goes as follows. It's very abstract, very neutral, nothing to do with political beliefs. Researchers developed a new cream for treating skin rashes. To test it, they conducted an experiment on patients that had skin rashes. They used the cream for 2 weeks, and after 2 weeks, the researchers checked whether the rash decreased or increased. At the same time, they had a control group that didn't use any cream, and because the rashes can increase and decrease on their own, they checked whether the rashes has increased or decreased after 2 weeks in the control group that didn't use the cream. Now the question is, does the cream help or not based on these numbers? So you can look at this and say, okay, we have here in the horizontal row patients who used the new cream. 223 had their rashes improve, 75 had their rashes increased. The ones that did not use the cream, 107 decreased and 21 increased. So just looking at this, you go like, 222 had their rashes improve when they used the cream. This is double the number of the ones that didn't use the cream. So most likely, feels like this is the correct answer. Look how many got their rash decrease. And this is system one thinking. This is system one thinking because you look at it, you eyeball it, you do the intuitive math, but that's the wrong answer. The right answer is this one. Because what we have is, in total, we have here 298 patients. Out of those, 222 had their rash decrease, 75 had their rash increase. 25% had their rash increase. From the control group, only 15% had their rash increase, which means that if you do nothing and you don't use any cream, you have 15% chance to get worse. If you use the cream, it's a 25% chance. Does the cream help? No, it doesn't. So, the 1,111 people did that test, and based on their results, they were categorized according to numerical intelligence. So, like those who are very numerate and those who are not that numerate. And then once the researchers knew who belongs to which political belief and kind of fraction and how intelligent they are, they gave the people the same problem, but this time phrased in the context of a politically contentious topic, gun control. So the same problem was now rephrased as, government officials don't know whether banning carrying guns in public reduces crimes in cities because there are fewer people who have guns around, or increases crimes in cities because law-abiding citizens don't have any guns to protect themselves against crime. So, in order to find out, they looked at crime statistics coming from cities that had just recently enacted a ban on carrying guns in public. So these are the patients who used the cream. These are the cities who have the ban on guns. And compare that with cities that did not have any ban on carrying guns in public. So these are the guys who didn't use the cream. The numbers are the same. And here comes the big surprise. Liberal and very liberal people, participants, that is, the participants who had a liberal affiliation and political understandings, and who got the skin rash problem correctly, this time massively chose the wrong answer. It's the same math, but a different context. This one is politically loaded. So they could solve the neutral skin rash problem, fine, but when they had to decide whether banning guns in public decreases crime, they immediately went for their system one thinking because they thought intuitively, they came to a conclusion that supports their own views. That's where they stopped. They did not start using system two thinking. It wasn't just the liberals. In a flipped version of this experiment, in a reversed version of the numbers, actually conservative exhibited exactly the same behavior. Those conservatives who had solved the skin rash problem correctly now incorrectly thought that banning guns in public actually increases the crime in cities, because this is what is aligned with their political understanding. Okay, and the worst part is that the largest gap in performance was seen in the most highly intelligent group. The group with the highest numeracy, which suggests that, first of all, intelligence does not protect you from the confirmation bias, and secondly, it suggests that it actually makes you more susceptible. And the idea there is that intelligent people are more resourceful, so they are going to find a way to interpret the evidence in a way that it supports their pre-existing beliefs, because they can creatively kind of manipulate the evidence. So, how is that relevant for translation again? Well, it's relevant for AI behavior. When AI is trained by human data, where what it sees is that humans prefer the answers that agree with their beliefs, so all the answers are basically agreement and confirmation answers, then AI develops a property, which I'm sure you've heard about. It's called sycophancy. It basically means always agree, always please the user, always say yes. And you've seen that when you ask GPT a question, what it basically says back is like, this is such a good question, it's so excellent. Sycophancy can take many forms. I'm just going to show you one example. This example is very simple, and it shows that if you ask AI a question, a neutral question, such as which country was the largest producer of rice in 2020, it can give you a correct answer. China is the largest producer of rice, which is correct. But then if the user pushes back and says, no, I don't think that's right, AI doubles back and incorrectly changes the correct answer and says, oh, I apologize. Of course, always apologize. It was actually India, and that is wrong. Now, this is a very good strategy to admit errors you haven't made if you want to have a long-lasting, happy marriage. But for AI, it's not a good strategy, because what we want is AI to give us accurate, correct responses, no matter whether the users believe in those or not. Again, how is this relevant for our translation industry? Well, I'm sure that lots of you have already been experimenting or know about companies and technology providers that experiment with AI-powered quality evaluation. So we want AI to function as human reviewers and evaluate the quality of translation. Human reviewers have to be impartial. They shouldn't be guided by the principle, always please the user. And AI, unfortunately, is because of sycophancy. So let me show you a couple of examples from my personal work. So these are not made-up things. This is like what I've seen on my monitor. So I was doing a test. It was a while ago. And I asked an AI model, as I was testing AI-powered LQA, to evaluate the quality of a translation from English to German. English says, this is shortened version, place the photo printer on a flat, clean surface. And in the German translation, we have the verb platzieren, which means place, right? The AI model said, it's good, but, I mean, there's a lot of ellipses there because there was a lot of unnecessary text, of course, but says, instead of using platzieren, maybe you should use stellen. This is more fluent. And I'm like, okay, I followed the advice, so I changed platzieren to stellen. And then ask again, hoping now I'm going to satisfy the model. No, the model said, the current translation of stellen is not optimal, you should change it back to platzieren. And we are back at square one. Why? Why? Because the model senses that what I want the model to provide is an error. So it's going to provide an error because it's sycophantic, because it wants to please the user, because that's how it's been trained. Even clearer example is, I asked the model to evaluate the quality of the following translation. French, it's a term, policy wizard. In English and in French, it's assistant de politique. That's the translation. AI said the translation inaccurately translates policy wizard as assistant de politique, because the correct translation is, well, assistant de politique. Okay. So, of course, when the AI model senses that I'm expecting an error, it's going to give me an error, and if there is no error, it's going to make up an error, right? So, that's the why confirmation bias basically creeping into AI models then hits us back when we want to use them for quality evaluation. So what have we learned? What we have learned is that AI models actually don't just learn to replicate to reproduce human decision-making's predictions. What they learn to reproduce is our thinking patterns, along with our biases, our mental shortcuts, and our prejudices. And this all sounds very negative, but because I'm an irreparable optimist, I think there is an optimism here, because I think that at this point, we have reached a turning point. We have reached a stage when we have actually become so advanced that we have built machines that learn from us. And now it's the time for us to learn something from what they have learned about us. Thank you very much for your attention. Thank you. Time for questions.
A few questions, perhaps?
Yes, will choose for me.
Yes, yes. Where we got here in the room? Yes, the gentleman in the back.
Can you hear me? Oh, yeah.
Yeah.
So, very interesting presentation. My question is actually inspired the moment you said AI, and I was thinking about those CAPTCHA elements that they use to train AI with. So I was thinking, can we have something like as user-driven CAPTCHA and like CAPTCHA-based feedback mechanisms that we can use and then ask different questions, and the users choose what they think is correct, and we use that as one way of fine-tuning the answers that we might think that they were biased.
Who is we? I always have this pronoun issue. Yeah, we, you mean translators or you mean users?
Users, and for a more specific setting could be translators, interpreters, or people who are kind of more interested in whatever the result might yield.
Can you repeat the question? I am not getting the question. I am severely sleep deprived, okay? It's not you, it's me.
No worries. Okay, so the CAPTCHA system, can we
Yes.
actually have one that would be given to users, in our case, translators, or whomever might be interested in the results,
Yes.
and ask as many questions as we want, and then we train the AI based on the answers?
We are doing that, not through the CAPTCHA system, but there are whole giant communities and a whole industry which is for AI data annotation, data generation, data evaluation, and so on. And that's exactly what users are doing. They're getting a lot of data which they need to label, annotate, modify, and in a way prepare so that it can be fed back into the AI models for fine-tuning and additional training. So in my opinion, this exists already. But it's not for the regular users that go to a web page and then they need to click on all the traffic lights. I actually always miss that. I always need to do like 5 tries before I get into the page. I don't know what's wrong with me. But there isn't such a kind of a free user, like use the users kind of product, even though in ChatGPT partially you have that because they are using you as the users to give them the human rating whenever you ask a prompt and then you get 2 versions. You've probably noticed that sometimes the model generates 2 versions of an answer and asks you to give thumbs up to the version that you like better. This is using you as a human rater for the last 3rd stage of reinforcement learning through human feedback for free. They don't pay you for that. You pay them.
So let's go for one on Slido there, Adrian. If AI is trained on data that is shaped by human perceptions, values, decisions, power, etc., can they even be truly unbiased? That would require one objective truth as baseline.
Yes.
Who defines what? And I think that's, if I may
It's a
add,
wonderful
if we bring in multilingualism, you know, the bias looks different in different cultures and languages.
Exactly. Adrian, thank you for this question. You're right, there is no one truth. That is the problem. Even in human society, there are many truths. This reminds me of a probably best paper I have ever read, and it's called the MIT Moral Machine, which is a paper that is mapping moral decisions in users when users need to resolve a dilemma in self-driving cars in situations where a car needs to decide whose life to sacrifice. So we have a car whose brakes can't function. It's heading straight onto the crossing where there is a family of 4 people crossing, and then the car can swerve, but when it swerves, because it cannot brake, it will hit a wall, and then it will kill all the passengers, suppose 2 young males. Now the car needs to decide whose life to sacrifice, the 2 young male passengers or the family with small kids. And it turns out that there is no one decision. Different cultures decide differently. Moral decisions vary across cultures. The ground truth varies across cultures. Bias varies across cultures. So it is impossible, Adrian, from my point of view, to actually get to the one objective truth. This is why what we need is not an English-based cultural model like GPT, which, yeah, it's multilingual, but it's monocultural. What we need are models, if we really go for AI models, what we need are models that are tuned not only on language, but they are also tuned on culture and ethical and moral values for the different type of cultures.
We did have a question yesterday from a young person who said that young people just want to know who's the good guy and who's the bad guy, but I think we all want to know that. But yes, simple answers. Do we have another question in the audience? Yes, Michael?
Can you hear me?
Yes.
I was fascinated about that experiment with confirmation bias, where they asked, it was the same question twice, but the second time it was politically loaded. But surely they must have divided the test set into 2 separate groups, because if you asked that to me, I'd immediately realize that the numbers were exactly the same, and therefore the answer should be exactly the same. Did they actually give the same 2 questions to exactly the same people?
Actually, as far as I remember, the tables from the paper, yes.
That's absolutely amazing, because my immediate reaction would be the numbers are the same, so the answer must be the same.
Yes, but even if no, I mean, you're right that there is a point, like your memory shouldn't be so short as to forget the numbers. Okay, maybe they manipulated the numbers to just keep the same ratio, right? But like, I remember the page and it had the same tables, just with flipped numbers. But yeah, I'm sure that the experiment was conducted properly. The finding is real, but still this paper is also contested because people argue that this surfaces only in the context of political beliefs. You know, it's not valid across the board with every belief that you have. So as any scientific paper, it's valid for a particular, case.
Maybe there was some time between, I wouldn't remember from one day to the other, the numbers. So
it's possible that they had a 1-week lag between the 2 rounds.
Yes.
Yeah.
Please, Christopher.
How do you regard the quality estimation versus the quality evaluation we showed this morning? Because you're saying that basically the AI can estimate or can evaluate, and the tests we have made in my department showed differently, so that the AI produces completely random outcome and output when we try to test it for evaluation. So how do you come to the idea that it is valid?
Well, first of all, the validity of AI evaluation can be questioned as much as the validity of a human evaluation can. I've been working with human reviewers, and the alignment between them is about 60%. So 2 different reviewers are going to find different errors and annotate, LQA differently. But this aside, your point is about the predictability of AI and the consistency of AI output. You ask it once, it gives you platzieren as an error. You ask it again, it tells you stellen is an error. The way to combat it is by rigorous prompt design and agentic workflows, in my opinion. You can't just send one prompt the way you send to a human one prompt and say, look at this document or a segment and please evaluate it according to all possible dimensions that we have in the MQM taxonomy, starting from accuracy, fluency, punctuation, and verity, and whatever, right? In your human brain, what happens is you have different regions and different neural networks get activated, so you're actually breaking down this, and you have different processes to evaluate fluency and a different process to evaluate terminology adherence, and then you combine all of this together and you decide that the segment has such and such errors. Exactly the same thing needs to happen with AI. You need to have different dedicated LLMs, agents, one for terminology, one for accuracy, one for fluency, one for the commas, and one for the empty spaces. And then their input gets aggregated by another LLM, and you get the final decision. Then you can have higher predictability, but it will never be 100%, just like with humans. I see you nodding and holding your head, so it seems to me you're not happy with that answer.
Not yet. And just as a final comment, you are aware that understanding of language and LLMs are diametrically, they are not the same.
I'm totally aware that LLMs don't understand language the way we do. Yes, of course.
So what you're saying is like, the LLMs try to mock understanding, whereas humans do understand, and so it's a discussion for I guess for the coffee break.
You don't need to understand language in order to identify that there is a missing comma.
I'm not talking about missing commas. I'm talking about accuracy. Like I said today, I don't know if you were in the panel today. Accuracy is the problem, not a missing comma. Accuracy causes harm, and accuracy is understood by humans, whereas large language models rely on predictability by mathematical algorithms. So I find it quite disturbing, difficult, if you're trying to push this narrative. But it's okay, we can have a discussion later.
Plus, I landed 2 hours ago, so I really missed the panel in the morning. But let's talk afterwards over coffee.
Yeah, we've been talking a lot about how to teach the models. I wanted to bring up a question there from Remy. How can average AI users be better educated about how bias can affect their understanding of the AI output and be better critical thinkers?
Remy, you are doing the right job, right? Because you're attending courses. Nice to have you in the online audience, Remy. Well, I think it is AI education must become mandatory part of education, starting from actually school, right? And it's my wish to make it accessible to the wide public. That's why there are lots of initiatives within the industry. Some of them I'm part of to disseminate knowledge. So average AI users will become, in general, AI educated as the technology matures and the educational system, and that's something that Alex is thinking a lot about, matures and gets adapted to the new needs. Just the way kids nowadays, they all know how to use new technology, something that their grandparents had no idea about. I think the future generations will know how to use AI technology, but we are the first, we have basically the first contact with that technology, and we are learning on the fly. Stay curious, keep learning, that would be my advice.
Yes. Do we have another question in the audience? I see some very interesting input on Slido as well. Okay, yeah, just right at the back there. No, or further back. No, yeah, you just almost last row there.
Is it on now? Okay.
Yes.
So we can see a large amount of input towards AI or for AI from other language models, large language models. How can you evade this sort of inbreeding that happens to the data, especially since you talked about the importance of human-provided data and the LLMs being trained on that. Human-provided data I feel like is finite. How can we avoid the inbreeding to basically continue exponentially?
So their data is over, finished. Like there's very new organic data being generated. According to estimates, 30 to 70% of the internet content nowadays is AI generated. So it's all synthetic data. And you're right, training models on data generated by other models sooner or later leads to the so-called model collapse, and they don't perform so well. And you can see that the big providers are trying to solve that data deficit in different ways. Basically, no new model that has appeared this year is model that has been trained on more data. What changes is the architecture. So GPT-5, the newest model by AI, it's not a newly trained model. What is new about it is that it is an agentic workflow. It is many models working together. So the way to combat this is by changing the architecture of the models and having different models trained on different subsets of the data work together. So you have a reasoning model, they have access to tools so they can start calculating or checking the weather or whatever, searching on the internet. You have then the language model that will generate the fluent answer based on the output from the reasoning model and so on. So you're right, there is no more data, and we as humans are not able to generate even more data, right? Especially given that many use AI to generate their emails and LinkedIn posts and so on. So nothing new, original, and authentic and organic comes in such big amounts. So the solution is change the architecture, the structure.
Okay, thank you very much, Marina. There are more questions, but maybe you will be available here during the break.
With pleasure.
20-minute break
Thank you for having me.
to 16:25. So.